Welcome to the fifth video on compressible fluid flow. In this video, we will see what are the different types of reference states used to simplify the compressible fluid flow problems. The reference states are defined in order to simplify the governing equations and write them in dimensionless forms. The reference state properties are used to non-dimensionalize the properties at any point in the fluid flow. By doing this, it makes us easy to handle these quantities during the numerical problems as well as in developing relationship and for derivations. The main two types of reference states used in compressible fluid flow are sonic state and stagnation state. Let's discuss the first reference state, that is the sonic state. Sonic state refers to the thermodynamic state of fluid where Mach number becomes equal to 1. This is also called as critical state or critical condition. This is a global reference state, that is, it occurs at a unique place, and the properties at that particular place alone is used for non-dimensionalizing the properties at other points of the flow field. It may or may not actually lie in the flow field. This will be explained later. Now, consider case 1, where we have a supersonic nozzle with inlet Mach number 0.4 and exit Mach number 2. That means the flow is getting converted to supersonic flow from subsonic flow. During this point, there is a region of least cross-section area which is known as the throat of the nozzle. It is seen that if the nozzle is operating at supersonic condition, then at the throat of the CD nozzle, Mach number becomes equal to 1. The properties corresponding to the throat then represents the sonic state or the critical state. These properties are represented with an asterisk symbol, that is P star, T star, H star, A star, C star, etc. Moving on to case 2, consider a converging duct which also acts as a nozzle. It has an inlet Mach number of 0.4 and exit Mach number of 0.8. We see that a sonic state is not obtained within the flow field under consideration. But if we extend this geometry as shown by the dashed lines, we can get Mach number equal to 1 downstream of the flow. But this region doesn't lie within the flow field, but still this point can be taken for non-dimensionalizing the properties within the flow field. So this is what I meant when I said that the critical reference state may or may not actually lie in the flow field. Moving on to our second reference state, that is the stagnation state. It is the thermodynamic state that would be reached for a given state of fluid at a particular point by isentropically decelerating the flow at that particular point to zero velocity at zero elevation. It is also referred to as total energy condition. It is also known as the total state or total condition. It is a local reference state, that is, it can be defined at any point where we would like to non-dimensionalize the properties. This is a hypothetical state because isentropic deceleration is not practically possible, but it can be attained with certain approximations. The actual state of the fluid at any point in the flow field is referred to as static state. The stagnation state corresponding to the static state is obtained by isentropic deceleration of the fluid. The stagnation state properties are represented with a suffix 0 or total, as shown in the slide. In our class, we will be using the suffix 0 to represent the stagnation state properties. Now consider a flow of fluid through a duct as shown in the slide. This is the flow direction. Now A represents a particular point in the fluid field. We can use a pressure sensor to measure the pressure at that particular point, which is referred to as static pressure corresponding to point A. By providing a temperature sensor, we can measure the temperature at that particular point, which is referred to as the static temperature at that particular point A. Now, in order to obtain the stagnation condition at point A, we have to isentropically decelerate the flow to zero velocity at zero elevation. So, we insert a pitot tube at the same elevation as that of point A, and the pitot tube is connected to a reservoir. The flow, when it hits the inlet of the reservoir, gets decelerated to zero velocity, and we obtain the stagnation condition, which is represented as 0A. Now, if we provide a pressure sensor and a temperature sensor at the reservoir, we will be measuring the stagnation pressure at that particular point and the stagnation temperature at that particular point. So, we see that the stagnation state can be assumed to be obtained by inserting a pitot tube that produces a stagnation state right in front of it. Now let's consider another point in the fluid flow field represented as point B. In order to get the stagnation condition at point B, we insert a pitot tube just upstream of the point B. Now if we place the respective sensors in the reservoir, we will get the stagnation properties corresponding to point B, and if we place the sensors near to the duct along the point B, we will get the static conditions corresponding to point B. The stagnation state can be defined for any point of interest. We see that we are defining it at point A, we have defined it at point B. If we want, we can define it at each and every point. We can even define stagnation state for a point where Mach number is equal to 1, that is a sonic state. We can define stagnation condition even for a sonic state. Because of this, it is referred to as a local reference state. The static condition and stagnation condition is related by an isentropic process. We already said that the static condition is related to stagnation condition by a isentropic process. That is, stagnation condition is obtained by isentropically decelerating the flow from the static condition. An example for stagnation condition is the condition of the fluid kept inside a reservoir or inside a settling chamber. In these regions, the fluid will be of negligible velocity, and we can say that the fluid is decelerated to zero velocity. Hence, the properties corresponding to the reservoir conditions and settling chamber conditions are taken as stagnation conditions. Now, out of the two reference states, the stagnation state, being a local state, is widely used in compressible fluid flow. Now, let us see what are the different stagnation properties and how we can obtain a relationship for each of them. Starting with the stagnation enthalpy. Stagnation enthalpy is defined as the enthalpy at a particular point of the flow field when The flow is isentropically decelerated to zero velocity at zero elevation. Now, consider the steady flow energy equation, which we have already studied in our first video lecture. Let A represent the static state of the fluid and 0A represent the corresponding stagnation state. For a stagnation state, the isentropic flow results in the heat transfer rate to be 0. It is placed at same elevation, so change due to elevation will be 0. This is a simple flow passing through a bent tube. There is no shaft work involved, so the shaft work term also reduces to 0. And finally, and most important term, the velocity at stagnation condition is 0. So the velocity at 0A is equal to 0. When we apply all these conditions to our steady flow energy equation, the equation reduces to the following form. This is H0A is equal to HA plus CA square by 2, where H0A represents the stagnation enthalpy corresponding to the stagnation state of point A, HA represents the static enthalpy, CA represents the velocity of fluid at point A. In general, for any point in the flow field, we can say that the stagnation enthalpy is equal to the sum of static enthalpy and kinetic energy at that particular point of the flow field. Please note, all these terms are defined for per unit mass of fluid flow. This equation is a very important equation and is known as adiabatic energy equation. It also goes by the name stagnation enthalpy equation. So we see that on the right hand side we have the sum of all energies at a particular point in the flow field, and this is equal to the stagnation enthalpy. Hence, we can say that stagnation enthalpy represents the total energy at a point in the flow field. So, recollect the point that the stagnation condition refers to the total energy condition which we discussed while defining the stagnation state. So we see that the stagnation condition corresponds to total energy possessed by the fluid at that particular point. So stagnation enthalpy is the maximum enthalpy that the fluid can attain at a particular point in the flow field. So this also represents the maximum energy. Moving on, we define the stagnation temperature. It is the temperature at any section in the fluid flow which is obtained when the fluid is isentropically decelerated to zero velocity at zero elevation. From adiabatic energy equation, we have the following relation. We know that for a perfect gas, enthalpy is equal to the product of specific heat at constant pressure and the absolute temperature. Substituting this, we obtain the second equation, and rearranging this equation, we can obtain an equation for the stagnation temperature. Now T0 represents the stagnation temperature, T represents the static temperature of the fluid at any particular point, and V square by 2 Cp also represents a temperature term. Remember, there should be dimensional homogeneity. So if all the terms are temperature, then V square by 2 Cp also represents temperature. And this value is known as velocity temperature or impact temperature. Please note that T0, that is the stagnation temperature, corresponds to the stagnation state, which is also the state of total energy. Hence, this is the maximum attainable temperature at any particular point in the flow field. Moving on, we define the stagnation pressure. The static pressure corresponding to the stagnation temperature is called the stagnation pressure. That is, when we place a pressure sensor to the reservoir which is connected to the pitot tube, the static pressure measured inside the reservoir gives us the stagnation pressure. Since it is an isentropic process, the stagnation pressure is related to stagnation temperature using the PVT relationship for an isentropic process as shown. Next, we have the stagnation density. It is the density corresponding to the stagnation temperature and stagnation pressure at that particular location. Here we can use the perfect gas equation, that is P is equal to rho RT in terms of stagnation conditions, or we can also use the PVT relationship for an isentropic process in order to obtain the equation for stagnation density. Apart from this, let us also define the stagnation velocity of sound. This is the sonic velocity or the sound velocity corresponding to stagnation state. This is given as A0 is equal to root of gamma r T0, and all we did was take the previous equation, simplified equation for the sound, and replace T with stagnation temperature T0. Now let us see how the stagnation properties are represented in a thermodynamic state coordinate system. We start with the HS diagram. Please note that the HS diagrams and TS diagrams are very important in the study of compressible fluid flow. Here we recollect the adiabatic energy equation, which is H0 is equal to H plus C square by 2. This is the HS diagram. Let A represent the static condition of the fluid. The corresponding enthalpy gives us the static enthalpy, and we get the corresponding entropy represented as SA. The blue line represents a constant pressure line in an HS diagram. So here it represents the static pressure PA. Now in order to obtain the stagnation condition, we have to move isentropically to a zero velocity. The isentropic processes in an HS diagram are represented with a vertical line. So we move vertically to reach the condition corresponding to the stagnation state for the static state A. It is represented as 0A. The corresponding enthalpy, we get the stagnation enthalpy. The entropy remains constant because it's an isentropic process. The pressure line passing through 0A gives us the stagnation pressure. Now the height till point A represents the static enthalpy, and the height till point 0A represents the stagnation enthalpy. The difference between the static enthalpy and stagnation enthalpy gives us the kinetic energy represented by the height between point A and 0A. Here we can make the following inferences. That is, if the kinetic energy is less, that means if the flow velocity is less, then the static point A lies more closer to the stagnation point 0A. That means for low velocities, that is for subsonic flow, the distance between static condition and stagnation condition will be less because the velocity is less thereby the kinetic energy is less. Whereas in case of supersonic flows, which are high speed flows, the kinetic energy component will be very high, and because of which the static point A will be lying further away from the stagnation point 0A. Now let us see how the stagnation property is represented in TS diagram. We recollect the following equation. This is the TS diagram. That A represents the static condition. The corresponding temperature gives us the static temperature, and we get the corresponding entropy SA. The pressure line passing through A gives us the static pressure. We move vertically up in order to get this corresponding stagnation condition represented as 0A. We get the corresponding temperature, which is the stagnation temperature, and the entropy remains the same because it is a isentropic process. The pressure line passing through 0A gives us the stagnation pressure. The height till point A represents the static temperature. The height till point 0A represents the stagnation temperature, and the difference gives us the velocity temperature. Do note that the stagnation temperature or the stagnation condition in general lies always above the static condition. This is because the stagnation condition refers to the maximum energy condition, so the energy level of stagnation points will be higher than that of the static energy points. Now let us obtain certain equations that relate the static state with stagnation state. These equations will help us to express static state in a non-dimensional form using the properties corresponding to its stagnation state. These will be useful in derivations and in solving numerical problems as mentioned earlier. Let's begin with obtaining an equation between the static and the stagnation temperature. The first equation, which was already obtained from the adiabatic energy equation, we have the stagnation temperature and the static temperature. But this is not yet in a non-dimensional form. In order to do that, we use the following relation, that is, for a perfect gas, we know that the specific heat at constant pressure is equal to gamma R by gamma minus 1. We substitute this here, and after rearranging we get this following equation, that is T0 by T is equal to 1 plus gamma minus 1 divided by 2 m square. Now we see that the static temperature has been expressed in a non-dimensional form using the stagnation temperature, and on right hand side we see that the terms are specific heat ratios and Mach number, which itself is a non-dimensional number. Hence we have been able to successfully non-dimensionalize the static temperature using stagnation temperature. And yes, moving on, we will obtain the equation between static pressure and stagnation pressure. That is, we know the relation connecting the static temperature and stagnation temperature, and we also know that the static condition is related to stagnation condition by an isentropic process. So using the following PVT relationship for an isentropic process, we can obtain the non-dimensional form for pressure of the fluid. It is P0 by P is equal to 1 plus gamma minus 1 divided by 2 m square, the whole raised to gamma by gamma minus 1. Similarly, we can also obtain the relationship connecting the static condition and stagnation condition corresponding to the density. From PV relationship for isentropic process, the density and temperature are related as shown here. From this, we obtain the non-dimensional form of density using the stagnation condition as shown in the final equation.